I want to continue our discussion of vapor pressure of solutions. And in a previous lecture, I talked about what happens to the vapor pressure of a solution when we add a non-volatile solute to a solvent. Here, I want to talk about what happens when the solute is also volatile, right? So solvents are, by their nature, volatile. Okay, so they tend to have weaker intermolecular forces that enable them to volatilize more easily than things like salts. Unlike non-volatile solutes, volatile solutes will contribute in an additive way to the vapor pressure of a solution. So we can actually calculate this in a similar way to how we use Dalton's law back in the gas chapter. The total vapor pressure of the solution is going to be equal to the vapor pressure of the volatile solute. Okay, so it's the vapor pressure of the volatile solute plus the vapor pressure of the solvent, which we just assume is volatile. And the way that we can quantify it is by kind of doing a partial pressure kind of thing, like Dalton's law. The mole fraction of the solute, let's just call it A, multiplied by the vapor pressure of the solute, plus the mole fraction of the solvent, let's just call it B, multiplied by the vapor pressure of the solvent. Now, we can even have more than two components. So you can just, if you have a bunch of volatile things mixed together, it's additive, and you would just add up the products of their mole fractions and their respective vapor pressures. So these would just be the mole fractions of the volatile components multiplied by their respective vapor pressures. So the overall vapor pressure of the solution is going to be kind of like a weighted average of the mole fraction of each species times their pure vapor pressures, all summed together. Let's try an example where we do a calculation with a volatile solvent situation. So in this example, we're mixing two hydrocarbons, pentene and hexane. Hydrocarbons are always going to be volatile. So when we mix two hydrocarbons together, we can kind of treat it as a volatile solute situation. So in this example, at 25 degrees Celsius, pentane, which has a formula of C5H12, has a vapor pressure of 511 torr. That's the vapor pressure of pure pentane. It has a density of 0.63 grams per milliliter. Hexane, slightly larger molecule, C6H14, has a vapor pressure of 150 torr and a density of 0.66 grams per milliliter. Now, if we mix 25 milliliters of pentane with 45 milliliters of hexane, what would be the vapor pressure of that mixture? What would be the vapor pressure of the solution? So here we clearly have two very similar components. They're both volatile hydrocarbons. Okay, these are molecules with relatively weak intermolecular forces. They're molecular, they're molecules, they're not ionic salts. So that means that we have to calculate the total vapor pressure by adding up the mole fractions of the components, so the mole fraction of pentene times the vapor pressure of pure pentane, plus the mole fraction of hexane times the vapor pressure of the pure hexane. Now, in the problem, I was given the vapor pressures of the pure solvents. So the time-intensive part really is figuring out what the mole fraction of each of them is. So if you recall, mole fraction is the number of moles of the component in question over the total number of moles. So if I have just pentane and hexane, the mole fraction of pentane is going to be equal to the number of moles of pentane over the number of moles of pentane plus the number of moles of hexane. So how do we figure that out? Well, in the problem, I was given the volume of pentane, and I was given the density of pentane, and I was given the formula of pentane. From the formula, I can get the molecular weight. So in order to calculate the number of moles of pentane, I can use the volume, multiply it by the density, 0.63 grams per mil, and that serves to get rid of the units of volume and leave me with grams. And then I can multiply it by the reciprocal of the molecular weight. So C5H12 is going to be 60 plus 12. That's about 72 grams per mole. Okay, so that's the reciprocal of the molecular weight. And that calculation will give me the number of moles of pentane. So if you do that arithmetic, you should get a number of 0.22 moles of pentane. I can do a similar calculation for hexane because I was given the volume of hexane, I was given its density, and I was given its formula. So I can calculate the number of moles of hexane as 45 mils times 0.66 grams per milliliter times the reciprocal of the molecular weight. So C6H14, that molecular weight is going to be about 86 grams per mole. And when I do that, I get 0.35 moles of hexane. So now that I know the total number of moles of each of these, I can go back and plug them in to the formula for mole fraction. Up here, for instance, the mole fraction is going to be 0.22 moles of pentane over the total, which is the 0.22 moles of pentane, plus the 0.35 moles of hexane. And that is going to give me a mole fraction of 0.39. Now remember, mole fraction is it's a fraction that varies between 0 and 1. It's a proportion, right? Since I have only two components here, I can figure out the mole fraction of hexane by subtracting that from 1. 1 minus 0.39 gives me the mole fraction of hexane, 0.61. Okay, and of course those need to add up to 1. I have only two components. Their mole fraction should add to 1. So I can now plug these in to the formula to figure out the total vapor pressure of the solution. Okay, so that was this formula up here. The vapor pressure of the solution is going to be equal to the mole fraction of each component multiplied by the vapor pressure of the pure compound. So the vapor pressure of hexane is 150 torr. The vapor pressure of pentane was 511 torr. So taking those two values, I'm going to calculate the total vapor pressure of the solution as the mole fraction of pentane, which is 0.39, multiplied by the vapor pressure of pentane, which was 511 torr. I'm going to add that to the product of the vapor pressure of the mole fraction of hexane, which is 0.61, times its vapor pressure, the vapor pressure of pure hexane, which is 150 torr. And that gives me a total vapor pressure of 291 torr for the solution. So I want you to notice the vapor pressure of pure pentane was 511. The vapor pressure of pure hexane was 150. When I mix them together, they both make their own contributions to the vapor pressure of the solution. And the vapor pressure of the solution is a number in between those two numbers. So notice 291 falls in between 511 and 150. This vapor pressure of the mixture of volatile components is essentially a weighted average of the individual vapor pressures, as you can see in this example.